Hello, welcome. In this short video, we are going to look at the general structure of the region of convergence of the Z transform. We are going to look at the general structure of the ROC, that is the region of convergence of a given Z transform, X of Z. So, basically the statement is, or the proposition is, so for a Z transform X of Z, which is basically the Z transform of a given signal X of n, so for a X of Z, the ROC, the region of convergence, is usually an annular, A-N-N-U-L-A-R, annular, that is basically a ring-like structure. That means, so basically the ROC is the annular region between two circles of radius of radii R2 and R1, that is the inner circle of radius R2 and the outer circle of radius R1. So that means mathematically it can be represented as R2 less than R less than R1. That is the region of convergence is between these two radii, where R is the absolute value of the variable Z. Now let us verify this proposition. That is, we are going to look at the proof for this proposition. So we are going to look at the proof. That is, start with the definition of the complex variable Z. That is, Z can be written as R into e power j theta, where R is the absolute value of the variable Z and theta is the phase term or the angle term. So the Z transform at this value of Z, that is where this value of Z, that is Z is equal to R into e power j theta, is clearly equal to the summation n is equal to minus infinity to plus infinity x of n, and then we have z power minus n, which is replaced by r into e power j theta. So we'll have r power minus n and e power minus j theta n. So that is the structure of the Z transform. Now we know that in the ROC, the region of convergence, the Z transform, that is X of Z, is absolutely less than infinity. So this is now based on the definition of X of Z and then value of Z equal to R into e power j theta, we can write that absolute value of X of Z, that is absolute value of X of Z, will be equal to absolute value of this summation, that is summation n is equal to minus infinity to plus infinity x of n r power minus n e power minus j theta n. So absolute value of this summation. Now the absolute value of this summation will be always less than the sum of the absolute values inside the summation. That is, this value is always going to be less than the sum of from n equal to minus infinity to plus infinity, the absolute values, that is absolute value of x of n, r power minus n, e power minus j theta n. So, and note that the absolute value of e power minus j theta n is always 1. So, this one is equal to the summation n is equal to minus infinity to plus infinity absolute value of x of n into r power minus n. So, the absolute value of x of z is always going to be less than the sum of the absolute values of x of n r power minus n. In other words, the function x of z will converge when this function, that is x of n into r power minus n, is absolutely summable. Therefore, x of z will converge if and only if this value x of n r power minus n is absolutely summable. So the problem now becomes, what are the values of R for which this product x of n into r power minus n is absolutely summable? That means we want to find the values of R for which this product is absolutely summable. Now we can write the absolute value of x of z. This absolute value of x of z is always less than or equal to the sum of n is equal to minus infinity to plus infinity absolute value of x of n r power minus n, which we actually just proved. And now this summation can be written as combination of two sums, that is the summation from minus infinity to minus 1 x of n r power minus n, and of course value, plus the summation from n equal to 0 to infinity absolute value of x of n divided by r power n. So this sum can be split as these two components. The first one is the anti-causal component and second one is the causal component. Now this can be rewritten as the summation by simply changing the variable. It can be rewritten as summation n is equal to 1 to infinity x of minus n into r power n plus, and this sum can be written as it is, that is the summation is from n equal to 0 to infinity x of n over r power n, and of course absolute value. So x of z, that is the absolute value of the z transform, is going to be less than or equal to the sum of these two components. Now it will converge when these two sums converge simultaneously. That means we have to find the region in z plane for which both of these sums converge. So let us call this sum number 1, and this sum number 2. So look at the sum number 1, that is summation n equal to 1 to infinity x of minus n r power n. You can clearly state that this product x of minus n into r power n, x of minus n into r power n will be absolutely summable, as long as this value becomes smaller and smaller with increasing values of n. That is, it will be absolutely summable as long as the value r is less than certain value r1. So that means as n becomes larger and larger, this value is supposed to be decaying. So in that case, this is absolutely summable. So that means this n equal to 1 to infinity x of minus n r power n will converge as long as it is inside a circle of radius r1. And note that of course r1 is less than or equal to infinity. So inside the circle of radius r1, this sum, that is the summation n equal to 1 to infinity absolute value of x of minus n r power n, this will be less than infinity, or it will be finite as long as this value becomes smaller and smaller with increasing n, or basically this is the radius r is inside a circle of radius r1. So the value r is inside a circle of radius r1. So the region of convergence will be basically a region inside the circle of radius r1. So this is the ROC, the circle of radius r1. So this is the ROC. So that is the ROC for the sum number 1. Similarly for the second sum, that is summation n equal to 0 to infinity x of n divided by r power n, and of course absolute value, this one will converge as long as this r power n, that is 1 by r power n, is a small value and does not become very large with increasing n, or at least this, or in other words, this ratio does not become too large with increasing n. So that will be possible only for a region that is outside a circle of radius r2. That is, it will be possible only for a region outside the circle of radius r2. So the region of convergence is basically the whole z plane outside the circle of radius r2. So the whole z plane is the ROC for this summation. But not the area inside the circle of a radius r2. So this is for the second sum, that is for sum 2, this will be the ROC. Now, but for the x of z, which is basically combination of both 1 and 2, that is, it is the sum from n equal to 1 to infinity, the absolute value of x of z is basically less than or equal to this summation x of minus n r power n plus the second sum, summation from n equal to 0 to infinity x of n divided by r power n, and of course absolute value. So the absolute value of x of z is less than or equal to these two sums. So that means it will converge as long as both of them are actually absolutely summable. That is, both x of minus n into r power n and x of n by r power n are absolutely summable, and that is possible only in a region that is intersection of these two ROCs, that is intersection of this ROC with this second ROC. That means it will be basically an annular region or a ring-like structure that is between these two circles, provided that R1 is definitely greater than R2. So provided or given, or if it is possible that R1 is definitely greater than R2, in that case the ROC for x of z, that is x of z's ROC, will be R2 less than or less than R1. That means it will be an annular region between circles of radius R1 and R2, provided R1 is of course greater than R2. Now to look at some examples, let us consider this Z transform, that is x of z is equal to a transform that is equal to 1 plus z inverse plus z power minus 2 and so on, in other words 1 by 1 minus z. So this Z transform has R2 equal to 0 and R1 equal to basically infinity. That means the ROC, the whole Z plane except the origin, is the ROC for this Z, for this x of z, and clearly R2 is 0 and R1 is infinity. And for x of z, that includes positive powers, that is z power 2 plus z plus 1 plus z inverse and so on. For this kind of Z transform, both the infinity and origin are excluded, and that means it will be the whole Z plane but excluding the origin and the infinity. That means R2 is 0, R1 is infinity, and the region does not include, the ROC does not include infinity and also does not include 0 or origin. And another important conclusion we can draw is that for anti-causal signals, that is for x of minus n's, the ROC is usually a region inside a circle of radius R1, and for causal signals the ROC is usually a region outside a circle of radius R2. So to summarize, we have looked at the general structure of the ROC of a Z transform. It is usually an annular region between two circles of radii R2 and R1, where R1 is greater than R2, and this can be proved based on the fact that the absolute value of the Z transform is less than two summations, where the first component is basically the summation of the product of x of minus n to r power n, where it basically corresponds to the anti-causal component, and the second sum corresponding to the causal component, that is x of n divided by r power n. And if these two sums converge, then x of z will also converge. And for the first sum, the region of convergence is basically an area inside a circle of radius, r1, and for the second sum it is the area outside a circle of radius r2, and for the whole x of z it will be the intersection of these two circles, which is basically given by an ring-like structure or annular structure between these two circles. And finally the ROC will be between R2 and R1, where R is the absolute value of Z. Thanks for watching.